Possible physical explanation for lattice confinement fusion presented by József Garay. This poster presentation is the continuation of my other poster titled The Phase Transformation of the Electron and the Structure of the Atom. You might want to see that first. The physical process of the fusion is extremely simple. You just have to bring the two nuclei into femtometer distance from each other and fusion will occur. There are two major obstacles which are supposed to be overcome. One, the repulsion of the positively charged nuclei should be eliminated. The physical process, how it's possible, is discussed in my other poster. You might want to see that first before you go further in this presentation. And the other obstacle, the two nuclei has to get to each other within a femtometer distance. This requires a very, very precise aiming. And how this is physically possible is discussed in this presentation. My other poster presentation describes in details how the electrons go through a phase transformation from point to surface charge and vice versa when they captured or freed from the atom. This surface charge electron shell can shield the nuclei and makes possible to overcome on the repulsion of the same charges. Please note that the shielding is effective only at low energy levels, specifically below the ionization energy, because then the shielding is gone. So lattice confinement fusion is possible only at very low energy. Stability of the electron shell in the atom. I was doing energy balance investigation of the electron shell, and it turned out that the stability of the electron shell is provided by the one-dimensional Casimir energy, which acts on the surface of the electron shell. It has been also shown that this one-dimensional Casimir energy is reproducing the ionization energy. If this model is correct, then if the neighboring atoms shielding the Casimir pressure on the electron shell, then the electron should be removed at lower energy than the ionization one. Both the photoelectric effect and the zero band gap energy is consistent with the suggested shielding effect on the stability of the electron. For free or individual atom, there is no shielding, none. Therefore, the ionization energy is required to remove an electron. If an atom situates on the surface of the metal, then it's about 50% of the surface is shielded by the neighboring atom. Thus, the energy required to remove an electron should be about half of the ionization energy, which is consistent with the measured work function of the photoelectric effect. Inside the metal, there is a complete shielding, so no energy should be required to remove an electron, which is consistent with the zero band gap energy and the C of the electrons model. The deformation of the electron shell in cavity or in defect. If the atom situates on the surface of a metal, then half of the surface is open and the Casimir pressure is acting on that, and the other half is surrounded by the neighboring atoms in the lattice. So the pressure on the atom will be spherically symmetric. However, if the atom gets into a bigger cavity or bigger defect than the size of the atom, then the pressure on the atom or the electron shell becomes non-spherically symmetric, and therefore the electron shell will deform. This deformation can be caused not only by the Casimir pressure, but like momentum change induced by electrolysis, diffusion, etc. If, let's say, two deuterium end up in a cavity of a palladium, then both of the deuterium will deform, and this deformation will go ahead until they get support from the side of the cavity or until they almost completely flattens out. If the cavity is too wide, and let's stick to the deuterium atoms, the two atoms flattens completely out, then the two protons, the two nucleus, most likely will find themselves far enough, not getting close enough for a fusion. On the other hand, if the cavity is narrow and the size not allow the deuterium electron shell to flatten out almost completely, then again the two nucleus will end up far from each other and fusion will not occur. If the size of the cavity is exactly the same as the size of the flattened out deuterium, then the two deuteriums will flatten out exactly the same way, and the two nuclei will end up very, very close to each other, and fusion might occur. This can be calculated, what is this cavity size, and it should be pi times the radius of the atom. If the nuclei are agitated, that would enhance the chance of the reaction of the fusion. This can be done by heat, increasing electric current, pulsation, triggering by atomic vibration, especially at resonant frequencies, magnetic field, and pressure. The reaction for lattice confinement fusion of deuterium is two deuteriums will fuse to helium-4 and releasing 23.8 megaelectron volt energy. This is an enormous energy, and in order to absorb this energy and transfer to the lattice, it would require at least 5 to 10 atomic layers. So the depth of the cavity should be a minimum of 1-2 nanometer. The energy absorbance and the transmission of the heat generated by the reaction sets a limit on the frequency of the possible nuclear reaction sites, cavities. In order to avoid the melting of the surface, the nuclear active sites, the cavities, should be at least 10 to 20 nanometer apart. The optimum size and depth and frequency, of course, it should be determined experimentally. Let's summarize the physics of the lattice confinement fusion process. The surface charge electron shell eliminates the repulsion of the protons, so that allows to get close enough without repulsion. In cavity, The non-symmetrical stress on the electron shell causes deformation of the electron shell. The result is same if the two electrons ending up in the same cavity. Controlling the size of the cavities, femtometer encounters of the nucleus can be achieved. The cavity has the right size for fusion if the cavity size is the same as the size of the flattened out electron shell of the atom. The process lattice confinement fusion can be enhanced by increasing the thermal energy, electric current, pulsation of the current, resonant frequency, etc. The absorption and transmission of the released energy sets limits on the depth and frequency of the nuclear active sites, cavities and defects. The proposed theoretical values for the size and frequency of the nuclear active site should be experimentally defined. Thank you for your attention.